Okay. Great. So it's a great pleasure to be back here. I would like to thank the organizers for the invitation for organizing this summer school. So what I'm gonna talk today and tomorrow are sort of a new way of thinking about scattering amplitudes. I don't know who first invented this name Surfaceology, but this way of thinking about amplitudes is based on something very, very simple. It's really just thinking all the curves on a given surface. So that surface tells you which order, like loop order, and also like 'T Hooft expansion. I'll explain all this in detail. Let me just give you a big overview of what I'm going to talk about. So this is this Surfaceology. As the name suggests, is about surfaces, but really it's about curves on surfaces. So you want to consider all possible curves on surfaces and write down some kind of integral over all these curves, which will give you scattering amplitudes. Okay? And let me give you some references. So basically, most of the things I'm going to talk about will be based on, let's see. So this paper, by Nima and the collaborators, and two more papers. So most of the things I will talk about can be found in these three papers. So today I'm going to focus on the first one, actually only a fraction of the first one, and then tomorrow I'll go to the other two. If you want some, let me see if I put this somewhere. Okay. Yeah, there's some old references from 2017. There's the ABHY paper, and from 2019, December of 2019, there's some follow-up of the ABHY paper. If you're interested, you can ask me. So I was asked to originally I was asked to talk about positive geometries, but that's too broad a topic. I can give you some idea of what are the positive geometries and the relation to surfaceology as an even bigger picture or overview. So we know that there's the usual way of thinking about scattering amplitudes. Okay. So you have some particle coming in, some particle going out. This amplitudes. So we can view it as, really summing over some processes that's given by Feynman diagrams. Okay. So this way is the usual way of thinking, and there's also another way of thinking about this, which is really considering I think you've heard from Alinda's lecture that you can also consider them from some worldsheet picture. Okay, that's the string way of thinking about scattering amplitude. So here you are really summing over all possible processes that happen locally in your space-time. So every step you have you have to put in what are the interaction vertices and so on. And here you are considering some CFT correlators on the worldsheet. Okay, and then that gives you string amplitude whose alpha prime to zero limit. So this is the inverse string tension, and the alpha prime to zero limit give you back the field theory amplitude. Okay. So this is really a broad overview of what this whole field is about. However, in last 10, 20 years, people have developed some new way of thinking about amplitude, not just a new way of calculating them, but really fundamentally different way of thinking about these amplitudes. So we want to get rid of Feynman diagram, and we also don't want to consider all this worldsheet physics, the CFT living in string theory. So here are some examples of this new way of thinking. For example, in the spatial theory called planar n equals 4 super Young mules, there is the amplitude hedron. So this is probably the most famous example of positive geometries for scattering amplitudes. So here we're thinking about some geometric object living in your kinematic space. For example, in this case, will be some twistor space of the dual of your momentum space. It's called a momentum twister. And if you think about some geometry living there, some kind of polytope or curvy version of the polytope, and then you can compute something I will explain later. You compute something called the canonical form of that polytope, which basically give you a rational function or a top dimensional form living in that kinematic space. That gives you the amplitudes in this special theory, and it's give you the all loop amplitudes, actually all loop integrand, the sum of all Feynman diagram. So here you think this way of thinking is very different from any traditional way of thinking, because you are not considering summing over Feynman diagram in any local space-time. Everything lives in basically at the boundary, at the boundary of your space-time or this kinematic space. You are directly formulating everything in terms of some geometric object whose canonical form give you the amplitude, all loop amplitude in this case. Okay, and of course there are many development. For example, remarkably, this is living in 4 dimension. If you just dimensional reduce this amplitude hedron to 3 dimension, to the external kinematics, you put it to live in 3 dimension. That gives you something very interesting. It gives you so-called ABJM amplitude hedron. That was only worked out. We only worked it out a few years ago. That turns out that the geometry that has 4-dimensional kinematics that describe n equals 4 super means all loop amplitude. If you reduce it to 3 dimensions, it gives you ABJM. And there are many other extensions. For example, you can go from amplitudes to correlation function, half BPS correlation function in n equals 4. That's also described by some geometry. So even off-shell, you consider purely off-shell object, which are 4-point correlation function also described. So this is the whole world of positive geometries that the rule of the game is not to write down Feynman diagram or consider worldsheet, but rather doing something very, very new to consider some geometry whose canonical form will compute all these things, okay? Of course, you might object. You say, okay, this is all about some very special theory. N equals 4, ABJM, they're very interesting, but what about more like non-supersymmetric theories, you know, plain Yang-Mills theory, or even like trace phi cube. I mean, let's consider this simplest, the color scalar theory. Okay, so trace phi cube, the Lagrangian of trace phi cube is given by roughly speaking, given by this. What about this kind of theory? It's even scalar theories, right? And they have no supersymmetry. Can you formulate it? So this is I would say the second wave of this thinking about positive geometries, but in a much simpler setting. Just consider this. This leads us to first to the ABHY associated hedron, and then to the surfaceology. So it's really this way of thinking, and of course, not only this field theory, but you try to alpha prime deform it to give you string theory. Okay, string amplitudes. So the thing I'm going to talk about, at least today, and also a lot of tomorrow's lecture, is about this simplest theory and its alpha prime deformation to some, say, tachyon amplitude or some scalar amplitude with fully fledged alpha prime corrections. Okay, in the string setting. So we want to think about a way of describing this. Of course, you may say, okay, what could be simpler than summing over Feynman diagram for phi cube theory, right? This is just summing over all possible planar cubic diagram. What's the Feynman rule of this? It's really giving you like, for 4 points, it's giving you these 2 diagrams. Everyone knows that this is the S channel, this is the T channel. Like for 4 point, this is the Feynman diagram. What could you do? And the alpha prime deformation is the famous beta function, right? So you have like alpha prime S, alpha prime S plus T, Veneziano amplitude. Okay, so really the most basic level, I'm gonna tell you how this surface idea or the positive geometry idea is explaining this kind of functions. This string amplitudes for scalars and its field theory limit that give you chase phi cube amplitudes. So this way of thinking that I'm going to introduce is a different way of thinking about this chase phi cube and string amplitudes without Feynman diagram or any worldsheet physics. It uses surfaces, but not any worldsheet physics, okay? And then tomorrow, I'm going to generalize. So this actually, very nicely, this contains theories such like nonlinear Sega model. This is about pion scattering, okay? By the way, this is also to all loops. I mean, the one very nice thing about this surfaceology is that once you work out chi level, you know about all loops because you're just changing your surfaces. So everything you consider here, you have to make them work for any surfaces, all the curves on any possible surfaces. Then if it's the same formulation that apply to chi level case, which is like a disk, and to all the higher genus corrections, then you're done. Then it must give you all loop. Otherwise, it won't give you the correct chi amplitude, right? So in a very precise sense, I'm going to tell you, I guess tomorrow, that all loop pion scattering amplitudes are contained in this chase phi cube amplitudes. And also the Yang-Mills. I mean, these are about gluon scattering in any space-time dimension without any supersymmetry. So this is not the special planar n equals 4. I mean, also all the non-planar corrections. Here we're not, the surfaces does not know about planarity. I mean, the planar sector is a particular simplest part of this surfaceology, but we can describe all loop non-planar gluon scattering in Yang-Mills theory. This will not be able to describe them. Of course, you cannot describe them using the chase phi cube. You have to describe them using the stringy chase phi cube. So once you have the alpha prime just the string amplitudes, it turns out that it contains the Yang-Mills amplitude in it. Okay, in a very simple way, I will show you how to just deform the kinematics of stringy chase phi cube, and then you get all the gluon scattering for free. So I'm sure some of you heard about this. This is really giving you some scaffolding gluons, where every gluon is described by a pair of scalars. So if you, instead of thinking like n gluon scattering, you are thinking about 2n or n pairs of scalar scattering. So it's very nice that the gluon scattering problem will be contained in 2n point phi cube amplitude, but with the string correction. So this is the general picture. Of course, how do we discover all this unity of the different colored particles? So one restriction of this whole surfaceology story is that we still don't know how to apply it to uncolored particles, like gravity, okay? That I have essentially nothing to say about. Gravity amplitudes, closed string amplitudes, you know, this, or even you ask me uncolored phi cube. It's a big open problem in this field. So everything is about colored particles. Here the chase phi cube, here is the nonlinear Sega model with colored, the pions are in some flavor group, and then the gluons are in the also colored. But we discovered this unity of colored particles like phi cube, pions, and gluons because we find that they have some common hidden properties. So this can reveal some very interesting property that I'll also describe tomorrow, that called hidden zeros and the factorization near zero or splitting near zeros of this all these amplitudes. Okay, so that's a big overview of what I'm gonna talk in this 2 sets of lectures. Any questions so far?
How much kernel are you?
So very general. So we're considering a generic SUN group where n is just generic. If you take n to be very large, to take n to infinity, then you'll go to the special planar sector of this. But in general, here is not any of the things I'm talking here is not sensitive to the gauge group. Okay? Yes. Very good question. So there is some way of so for example, for the simplest case of like Yukawa coupling, you can think of this in the same way of I'll describe later that actually, for general colored theories with any Lagrangian, this particular way of thinking about, at least at tree level, this particular way of thinking about the coming from surface, you take the field theory limit, which is known as the tropical limit of some string amplitude, also apply to very general Lagrangians. But we do not have a picture for all loop scattering with, like QCD or this kind of realistic theories. We still don't have. Yeah. Other questions? Okay, so I'll begin. I think it's a good idea to ask a very basic question. So even in this, so everything I'm gonna say today will be about trace phi cube and its string deformation. Okay. So very basic idea. Why do we care about surface? Very big, very basic question, right? Why do we care about surfaces when talking about amplitudes? Okay, so you already see, like for trace phi cube, what are the amplitudes? The amplitude, I mean, tree level, loop levels, because it's literally summing over the Feynman diagram here is just the trivalent graphs where you only have your propagator, right? P squared, P1 squared, I mean, some propagator, product of some propagator. This is not individual particles, but sum of some particles. So it's very simple. This amplitude itself is very simple. But when you sum it over all the trivalent graphs, an equivalent way of thinking about them is really you're summing over some triangulation of a surface. So that's the most basic idea. So these two diagrams, need some color chalk. This X channel and T channel diagram I have here can be viewed of as triangulating this disk with 4 marked points, right? So you have 1, 2, 3, 4. What's your triangulation here? I mean, triangulation means that you find some chords or curves here such that the whole surface become some union of triangles. There's no, of course, you cannot cross those curves. So the triangulation here really means that triangulation means you have maximal number of non-intersecting chords. Okay, so this is one triangulation, and another triangulation would be just the opposite, right? So you have this. Okay, so how are this related to that side? So you really should think about this dual graph, where, for example, I mean, here is like a convention that between this mark point 1, mark point 2, I have my particle 1. Okay, here I have particle 2, particle 3, particle 4. So this triangulation, where I have a chord 1, 3, I have a chord connecting mark point 1 to 3, is really dual to a S-channel diagram, where you have your P1 and P2, and this chord itself is due to this S-channel propagator, right? And similarly here, this diagram, I'm saying something very, very trivial here, just to set up the stage that this will be like P4 plus P1 is in this propagator. So this is the T-channel diagram. And if you are not familiar with this general, with triangulation, here are some examples, right? So we have like even 5-point. What are the triangulations? The 5-point triangulations, you can, for example, have 1, 3, 1, 4. This is a triangulation because it divides the whole pentagon into 3 triangles. And the dual of this graph is nothing but this cubic diagram, right? Okay? So this cubic diagram, you have this moment, this propagator is like P1 plus P2 squared. And this propagator is P1 plus P2 plus P3 squared. Or equivalently is P4 plus P5 squared. Right? So the second one, because I'm putting my momentum here. This is P1, P2, P3, P4, and P5. Okay. So this is the very familiar thing that for any amplitudes, colored amplitudes, but particularly in trace phi cube, the propagator structure is really mimicking the triangulation of an angle. Okay? So you have, for 5 point, you have 2 propagators, and for n point, generally you have n-3 propagators. So for tree level, you really can have n-3 propagators or chords that are non-intersecting. Once you have this n-3 propagators, you cannot add any extra ones. They will definitely cross. So this is why it's the maximal number of propagators. Okay? So anyone know that how many triangulations or how many Feynman diagrams we can have for this pentagon case? Yes? Oh, okay, sorry. I will not use blue color. Oh, here's my red chart. That's a problem. Sorry. So for the pentagon case, we can have 5 possibilities, right? So this is 1, but all the others are just the cyclic rotation of this, right? So we can have the next one, which is like 1, 2, 3, 4, 5. But we start from 2 that can be connected to 4 or 5, and then we have 3 more. So five such triangulations. And for 6 particles, I mean, if you want, this is really a very simple game to play yourself. If you have not played with it, I mean, I imagine this is something you could, play as a kid. That you can have this kind of triangulation, right? So it's very similar to before, but you also can have, say, this kind of triangulation. I mean, like 1 to 3, and 3 back to 6, 6 to 4, right? Or you could have this kind of triangulation. 1, 3, 5. That's also a triangulation. In all these cases, you're dividing your hexagon into 4 triangles with 3 non-intersecting chords. So n-3 chords here, right? And here we had 5 Feynman diagrams, or 5 triangulations. Here, how many? Anyone? Very good. You have 6 images like this, 6 images like this, and only 2 like this, right? So they add up to 14 triangulations. This is the Catalan number, okay? So you've learned the first thing. As a kid, you should probably already learn this, that when you do trace phi cube theory, you're summing over Catalan number of triangulations of an angle. Very simple, okay? What do this have anything to do with surfaces? I mean, for this, we have to go slightly 1 step further. So here you're just playing with trivalent graphs and this duality with the triangulation of angle. I mean, you haven't really go to loops, right? If you go to loops, you'll find it's much more interesting. That I can give you some loop example also. Sorry. So let me give you an example at 1 loop. So for 1 loop, in addition to your external particles, say 1, 2, 3, 4, you can also have internal punctures here. That's where you basically where the loop comes from, right? So when I say surfaces, the simplest case would be I have some n marked points on the boundary, and then I have some punctures inside, L punctures inside that represents the L loops. For example, for 1 loop, I'll have 1 puncture here. This puncture is not an external point. And what are the possible triangulations? I mean, you can draw. This is 1 triangulation. All right? So you connect every external one to the boundary. This corresponding to a box diagram, the dual of a box diagram, or an n-gon if you want, if you have n points, because if you draw this, then it's the dual looks like this, right? Anyway, this is P1, P2, P3, P4. Now the propagator contains loop momentum, right? So if you call this guy like L, this guy will be like L plus P1 squared, L plus P1 plus P2 squared, and so on. Okay? So this is how triangulation of surfaces with, not only external marked points, but also punctures representing loop. This is still planar case. The most general planar case will be n marked points on outside and some punctures here. You can also play with non-planar surfaces and so on. So their triangulations are in one-to-one correspondence with this trivalent diagrams in general. But to describe the story really, to really define surfaces and curves on it and how we perform integral over these curves, I need to introduce one more thing, which is fat graph. Okay, so this will really answer my question. Why do we care about surfaces when we think about trace phi cube amplitude? Since trace phi cube amplitude, I'll just erase it, involve this phi, which is n by n matrix, right? So this phi field are really n by n matrix. So if you follow its indices, the interaction vertices really looks like that. So if you follow all the color flow, this is the so-called fat graph. So instead of drawing the thin trivalent vertices, I'm really fattening it to this ribbon graph or fat graph. Okay, and this is a very I think is the most important thing in this at this stage, which is all these triangulations you have really look like a surface. So for example, the 4-point one would look like this, right? So this is my momentum particle P1, P2, P3, P4. But really, what are the marked points? So the marked points are here. This is my marked point 1, 2, 3, and 4. So you see, doing a fat graph, drawing a fat graph makes it much cleaner that this is a disk with 4 marked points. The only thing I did is just making this marked points or this region bigger, right? So if you shrink it down to 1 point, this is literally a disk with 4 marked points. I'm just drawing it this way. So this represents a very interesting thing. I can draw one triangulation. I don't have to draw any other triangulation, just one triangulation that at the same time giving me one particular Feynman diagram for the trace phi cube, but also defines my surface, right? So for example, this one loop case would look like that. This box diagram in fat graph looks like this. Okay? So I have my mark points 1, 2, 3, and 4. And also my puncture here. Let me call it X. Okay? You can keep playing this game that how the fat graphs look like for 5 particles, it looks like this, and so on. Right? This is the fat graph for 5 particles. You have your marked points, and you can draw some non-planar diagrams like this. Sorry. Right? This will be really. Or maybe I draw it this way. I make it even more generic. Okay. This will be like a double trace amplitude where you have some external points on the one trace and also this two other legs on another trace. Anyway, so this is really the first point that when you consider surfaces, you are really giving me a particular triangulation that I will call the base triangulation. So you draw a fat graph, which is considered as a base triangulation, and it also defines my surface, right? This is just my surface in a particular base triangulation. Okay? So the number of propagators here are called E, the number of edges, not including external one, really the edges here, is equal to the famous n minus 3, well, n plus 3 times L minus 1. This is the loop order. Okay, so at L loop, you have this n plus 3L minus 1. So at tree level, this recover this n minus 3 propagator. That's the maximum number of propagator you can, chords you can have in a triangle. At the one loop, you can have n propagator, and so on. Okay. So let me. This is the definition of all the surfaces. Okay. Is there any question? Yeah. I mean, originally these diagrams are designed to follow all the color indices. So more precisely, if you draw fat graphs, you need to put arrows here, and the arrows represent how the color indices contract with each other. But here, for our purposes, we don't need to do that even. So this is actually what we really do is this ribbon graph. We forget about all the indices, and you're right. So different surfaces will come with different color factor with these traces. So for example, all the planar ones can come with a single trace, and the non-planar ones can have double trace, and so on. In this case, you will see that you follow the color flow, it will produce you a double trace of four particles living in one trace and two additional particles living in another trace. Yes. Okay, so that's why I said from very beginning, this is all colored particle. So very good. So yeah, this question is related to the previous question that, strictly speaking, I'm summing over all trivalent graphs with all orderings and so on, coming with different color factors. But as you know very well, you should first do a color decomposition. So here I'm really considering like tree amplitude of this particular color ordering, right? So I'm already fixing a color ordering. So all the mark points on the boundary of my disk is in a particular ordering. Of course, I can sum over other orderings. That's just there's no new information there. I just focus on one. At loop level is more interesting. You can have multi-trace amplitude and so on. So everything I'm talking about here are applied to the color stripped amplitudes, which are already fixed in some Tohuth expansion order. Any other questions?
Surface is not clear to me. Which is surface in the real world?
Sorry, which?
The surface, what you mean is not clear for me. In the real world, what are the surfaces are you talking about?
What are the
surfaces are you talking about?
Surface. Sorry, surface. This is the surface. So this is a two-dimensional surface, which looks like a disk with 5 small regions on the boundary, right? This is another surface. I mean, this is a surface where you have an internal puncture. They have all different order in the Tohuth expansion. Okay. So next, I'm going to define you curves on the surfaces. What are the curves on surfaces? So really, the game here is very simple. I have 3 definitions. Okay. Sorry.
When we're speaking about this triangulation, we're speaking only about planar graph, right?
No. This is a non-planar graph.
Yes, but when we're doing triangulation.
Yes, that's why I introduced fat graph. So if you do this way, you cannot do non-planar graphs. But if you introduce fat graph, then you can. Yeah.
For now, okay, about triangulation.
No, you okay. So I'm going to tell you next that even for this non-planar graphs, you can still define what are the non-intersecting chords here. So you can still do it, but you have to start from this surface. It's triangulation of the surface, not a triangulation of an angle. This tree level idea. Yes. It's still fine. For any non-planar surfaces, you can define a maximal number of non-intersecting chords, which make it a union of triangles. So that's still a triangulation of the surface. Okay?
Well defined, something is not colored?
No. So everything is colored. Yes. And in particular, everything I'm talking here, because I don't care about numerator now. I'm really talking about this propagator structure. Everything I'm talking today will be trace phi q and the string amplitude. Okay? Wow, I talked more than half an hour about this. So what are the curves next? What are the curves on surfaces? So you already see those curves, right? So when you define a base triangulation, these chords are already give you some idea of these curves. So in general, you would say, okay, a curve is to some So for example, this 1, 3 is like a curve. This is something that go from one puncture to another puncture. But as you can see, it's not very nice. So we'd rather do something called a lamination to make the curve really sitting on the surface. What is lamination? So I just slightly rotate the starting point of my curve clockwise. So when I say I want the curve from mark point 1 to 3, I really start from this momentum 1. And then I flow. And when I say I want to end on 3, I also do a clockwise slight rotation, because this whole region is just one point, remember, okay? So then I end up here. So this defines a curve, okay? So for any surfaces, I can start with any points, including external ones, internal punctures, but I slightly rotate it. For example, here I can go like this. I can directly go here, or I can go like this, or I can go even more. Anyway, so this is like the basic definition of the curves. And then there's a way to read off the kinematics or the momenta, kinematic invariance, or the momentum squared for any curve. So this already mentioned here that when you have a curve from 1 to 3, the momentum running associated with this curve is really dual to this propagator, which is P1 plus P2. And we want the kinematic invariance, so a Lorentz invariance, so we take P1 plus P2 squared. Okay? So I'm going to call this curve C, and the kinematic invariance associated with C will be called XC, which is some momentum associated with that curve squared. How do you associate with the momentum? It's also a very clear rule here, that you begin with the momentum you start, and remember, every time you turn right, you add the momentum from the left. Okay? So this rule may seem a little bit strange, but that's exactly what we did at tree level. Let me show again, say for 5-point example. So this curve is called 1, 3, right? Connected 1 and 3. So I have x13, which is really P1 plus P2 squared. How do I see that? I see it from the curve here. So remember, 1, 3 is going from this lamination to here and end here, right? So the momentum associated with this curve is really this P1, that's my beginning. And at this intersection, I didn't turn left, I turned right. So I can have this momentum P2 from the left adding in. But at this intersection, I already turned left. I leave the surface, so I don't add the momentum. So this is the general rule. You can also check yourself at one loop. This gives you correctly every propagator that I show for the box diagram is given by the correct momentum assignment. Okay, so I hope this is clear that I give you a surface. I can define any curve there with this lamination. The lamination is really just make it look nicer, that you don't start from somewhere here, but really slightly rotate clockwise. And then there's a rule for assigning a momentum with any curve whose square gives me a kinematic invariance called xc, the kinematic variable for that curve. Okay? So remember, at tree level, all these curves are nothing but diagonals or chords of my angle, right? So what is xij? Xij is always pi plus 1 all the way to pj minus 1 squared. This is the tree level planar variables, where I and j, I minus j has to be bigger than 1. Because if you go from I to I plus 1, yeah, we can also talk about this curve. If I come in at 1 and go out at 2, it's not interesting. This is called a boundary curve, right? So my curves are defined, I only care about those curves that are not homologous to each other. So this boundary curve, I go in at 1 and out 2 can be deformed just to the boundary. So what is xii plus 1? Xii plus 1 is nothing but pi squared, which by my condition is either 0 or generally m squared. It's just not a kinematic variable. It's just the external that. So I have to have I and j separated by at least 1, and then this is the, you can check yourself that this is the rule I gave you, which generalizes to all curves on all surfaces, but at tree level, this will be the planar variable xij. It's very important for us, okay? Yeah. Very good, very good. I'll come to this point. So naively you say, okay, there are infinite number of curves, right? So that's exactly related to your point. So I can go around many times here until I hit this. And we're very familiar with this fact that they are all assigned with the same momentum, right? So however times you round around, this is just that the momentum conservation tells you every time you pick a 0. So really, when I talk about curves on surfaces, there are infinite number of them. But when you assign momentum, it's going to be only finite number of them. So it's really this rule will tell you that however number of times you wander around, it's always given by the same momentum. So when I say amplitudes equals to summing over all these trivalent graphs, this is fine. But when I translate these trivalent graphs to triangulations at loop level, I have to be very careful because I'm really summing over infinite number of triangulations. So there's something called mapping class group that I have to mod out. Okay, I won't go into detail here, but it's just safe to say that if you literally follow my prescription, saying, okay, I give you a surface and I summing over all possible triangulation of the surface, I get infinite copy of the amplitude because every time I wander around, I pick up the same graph, and yeah. So I don't want to get ahead of myself. I'll talk about loop cases in a second, but let me first tell you what happens at tree level. Okay. So I think the rest of this lecture will be devoted to even just the. Well, let me write down the general formula for you first. So the general formula. So my promise is to tell you a basic idea what are the surfaceology. So this is the surfaceology. Curve integral. Just this one formula. All the rest of my talk will be trying to explain this formula. This is a string amplitude with alpha prime, and it's associated with a surface S. Okay, any surface. For any surface, I can define a string amplitude associated with it, which has this prefactor that alpha prime to the E. E is the number of propagator of a surface. And then I have some integrals for some integration variable dyi. This dyi is associated with every chord of the diagram that I'll explain later. Every one of them is integrated from 0 to infinity. And I have this very interesting factor that I take the product of all curves on the surface S. Okay? And there's a very interesting function of y. This is a rational function of y we call u variable. So basically all my lecture today will be explaining to you how to get u variable. Raised to the power of alpha prime xc, where xc is the kinematic invariance I defined. Okay? So if someone asks you what is surfaceology, what are the curve integrals? This is it. Okay? Just yeah, we're done. So of course I need to explain to you what are these variables. This is called a positive parameterization of my space of the curves. And this will be the u variables. That's the key to everything. The u variables satisfy a beautiful equation called u equations. This will be explained in detail in the rest of my talk. I just want to give you the idea that the u equation satisfies this property that any u variable of any curve plus the product of all the curves that intersect with this curve raised to the power of their intersection number. I mean, just how many times they intersect equals 1. So this is the key. This is the key to everything. So why the surfaceology works for give you all the amplitude and so this is so-called binary geometries. which, by the way, even in the early days of string theory, I'm sure you heard, so this factor in the early days of string theory, this whole factor of at tree level for the disk, sorry, this whole factor is known as the Koba-Nielsen factor. Okay, this is the particular. Sorry, I'm being stupid. This is sorry, dy over yi. Very crucially, this is the logarithmic form on this space, which has logarithmic singularities on all the boundary. I'll explain. But this is literally the string Koba-Nielsen factor if you restrict to the disk case. But now we have a generalization to all surfaces. That's the thing. And then of course you can also take, say, alpha prime to 0 limit of this. You get some field theory amplitude, which will be given by some tropical limit that are not right here. So anyway, so this is this is the very big idea of how surfaceology works. So in the rest of my lecture, I'll just define how to because I already explained this. For any curve, you can have some. So in general, this is an infinite product, right? You can see there are infinite number of curves. So this is an infinite product. There are infinite number of UC here, but they're given by a very well-defined rule that I'll explain. And that's it. So before I really dive in the general definition, I want to give you the tree level case. So the tree level case was understood way before this whole surfaceology stuff. I mean, first of all, the disk case is literally the original Koba-Nielsen string integral that they wrote down in the 60s. And they also actually knew about these U variables. These U variables are, for them, is the cross ratios, a special set of cross ratios in the worldsheet. And then also in this ABHY paper, we understand how tree level string amplitudes is formulated in this way, and their alpha prime to 0 limit is given by that ABHY associahedron. Yeah.
Can you determine the U uniquely or?
Yes. So once you give me a set of y, which are associated with a base triangulation, so basically y live in these edges. So there are e of y, right? So for every edge, I have an integration variable y1, y2, and so on. And then once you give me a particular way of representing the surface, the u's are unique. Every u is a unique function of this y. I'll give you the rule later. But let me go back to tree level, okay? Any other questions? For now, y just integration variables, some positive variables that I'll explain later, okay? So at tree level, this integral was known from the 70s, I think, as the Koba-Nielsen integral. It's this integral. I'm sure you already heard something similar, but let me just write it down for you. Z12, Z23, all the way to Zn1. And the product of all the ij, Zij raised to the power alpha prime Sij, right? Where Sij is the Mandelstam variables, and the Zij is just the Zi minus Zj. Okay? So I'm assuming you are familiar with the story that there is this integral at tree level. So this is really a tree level string integral. So the surface is really a disk with punctures Z1, Z2, and so on, okay? And the integration domains, of course, all the Z's are ordered. All the Z's are Z1, Zi smaller than Zi plus 1. This is the integration domain. So there's a tree level alpha prime deformed amplitude. This whole thing is called the Park-Taylor form. This looks like a Park-Taylor factor on the worldsheet. I mean, in string theory, in Amplitudes string CHY, this is all very important building blocks. This is literally the Koba-Nielsen factor, right? We're taking the product over all the Zi minus Zj raised to the power of Mandelstam, alpha prime Sij. Okay? So in this story, I don't need to tell you how, I mean, later I'll give you that, but just as the motivation, let me just, I won't prove it, but you can see very easily that this product is nothing but uij raised to alpha prime xij at tree level, where ij satisfies this thing, right? So I'm taking, so okay, I forgot to say here that how many xij are there? There are n choose 2 minus this trivial ones, minus n. So there are this number, n times n minus 3 over 2. This is the number of curves on a n disk with n marked points, right? So at tree level, this is the only case that's finite number of curves, and starting loops, there will be infinite number of curves. So at tree level, that's why everything is so clean here that you have Koba-Nielsen factor written as the u to the x. X is defined here, a planar variable, and u is defined like that, right? U is literally a cross ratio. It's zi minus 1j, zij minus 1, zi minus 1j minus 1, and zij. Okay, so what cross ratio is it? It's really like looking at I minus 1i, so I minus 1 and I, j minus 1 j, and you look at this cross ratio. You take these two guys and divide them by these two guys. Okay, so it's really a skinny rectangle of your whole disk, of your n-gon, and then you define this uij. The uij is associated with only the neighboring points. The cross ratio formed by this neighboring, these two pairs, I minus 1i, j minus 1j. So I leave you as an exercise to show this, and the key to show this is to find the linear transformation between Sij and Xij, right? So this is the, yeah. This is the key in showing, this is the key in showing this identity, that the Koba-Nielsen factor is nothing but all the uij to xij, where uij are defined as these cross ratios. So strictly speaking, this is not a linear transformation because all the Sij satisfy momentum conservation, right? Summing over j different from I. For any I, Sij satisfy this momentum conservation. I'm sure you know it. So there are n choose 2. So this product is really over n choose 2, guys. N choose 2 Sij, where there's only n choose 2 minus n x. I mean, the reason is that x's are all independent, linearly independent. Sij satisfy these n conditions, so they have the same number. Okay, so this reflects a very important point about already tree level, the use of u variables. The z's has this gauge redundancy, has this SL2C redundancy, because you have n points on the boundary of a disk. You can use this redundancy to fix 3 of the points, right? So this integration is really n minus 3 integrations, as you know very well, this integration over nz mod SL2, while our u don't have that redundancy. So u provides you a gauge invariant description of your n punctures with a disk. So strictly speaking, I'm not done because I need to translate all this u. These u's are not independent, right? I mean, the u's are linearly, the u's are gauge invariant objects, but they are functions of y. So I haven't introduced y, but let me just be very sloppy and tell you that I'll explain it later that there's a product of n minus 3 dy over y. This is the particular factor. So the particular factor turns out to be this very simple logarithmic form, and then you have this ij, uij to the xij. Okay? So I haven't explained how u are defined in terms of y. I'm just telling you that already at tree level, there is this rewriting. And this u already satisfies very beautiful u equations. Let me show you. So every uij, so it's this special case of the general u equation. This is the central theorem. This is the main results of. So I'm quoting Nima. He's saying that if you want to figure out what he has done with the last 5 years of his life, just this equation. So today I'm giving you more information. I mean, what he said is that if you are left in a desert and want to figure out everything that he has spent 5 years on, I will give you, he will give you that equation. So for every curve, there's a u, and the u plus all the curve intersecting with that, with the intersection number equals 1. you can figure out everything starting from that equation, right? So that's the central thing. But at tree level, this is actually well known. This is very, very simple equations that all the KL intersect with IJ raised to power 1, because at tree level, all the curve can either not intersect or intersect only once, right? I'm taking only those curves that intersect IJ, and when they intersect, of course, intersection number is 1. So the second exercise I'm leaving you is to prove this. It's a very simple proof. Just plug in the definition of the U in terms of cross ratio. You can show this, okay? So like let's even look at some example. Like 4 point. 4 point is really trivial. I have 2U, right? So U13 plus U24 equals 1. That's the 4-point U equation. Okay? And for 5 point, it's slightly more interesting. Like you have a curve U13. There are two curves intersecting it. 2,4 and 2,5, right? So I have U13, this is 4 point. This is 5 point. I have U13 plus U24, U25 equals 1. And of course, for 4 point, there's nothing. If you look at the equation for U24, it's the same equation, right? U24 plus U13 equals 1. But for 5 point, there are 5 more equations. For example, U24. Anyone tell me what are these two guys? U24 plus, I mean, you just draw your 2, 4 curve here, right? And 1, 2, 3, 4, 5. What are the curves intersecting 2, 4? 1, 5 is not a curve. 1, 3 and 3, 5, right? So you have 1, 3, 3, 5 equals 1, and cyclic. Okay? So that's the 5-point U equation, and so on. So you immediately realize one thing. There are same number of equations. So for example, I mean, also from here, right? Most generally, there are same number of equations and number of variables. For every curve, I have a U variable, but I'll also have a U equation. So it's already a non-trivial thing that these equations are not all independent. So there's a solution space which is exactly E-dimensional for any surface. In particular, for tree level, although I have same number of U variables as equations, those equations are not independent. Like 4 point, there are 2 equations that are the same. 5 point, there are 5 equations. If you solve them, you find a 2-dimensional solution space, because n minus 3 is 2 now, right? So these U equations lead you to some n minus 3 dimensional solution space. Here is one solution. I'm parameterizing all my U in terms of, you say n z's, no, n minus 3 z's, because there's a SL2 that I fixed 3 guys. But there's a more invariant way that I'm going to teach you later that I can parameterize all my U in terms of some positive parameter. The positive parameter is, there's no gauge redundancy. It's strictly given by, given any base triangulation, is strictly given by n minus 3 y's. Okay? So let me really write down the 4-point amplitude for you, which you will immediately recognize, right? So what is my 4-point amplitude? So in the original form, it's really dz2 over z2, 1 minus z2, where z2 is between 0 and 1. So I'm doing this gauge fixing of z1 is 0, z3 is 1, and z4 is infinity. So the only thing I have is z2. That's a 1-dimensional integral. That's what I mean by mod volume of SL2, and this particular factor now becomes just the z2 minus z1, which is z2, z3 minus z2, which is 1 minus z2. So you see that this particular factor indeed has 2 singularities, that when z2 approaches z1 or z2 approaches z3. And then you have this z2 raised to the power alpha prime s, and 1 minus z2 raised to the power alpha prime t. Okay? So in this case, it's particularly simple. I did a change of variable which make this form look like dy over y. And now I have two U variables, U13 to the alpha prime x13, which is s, U24 to the alpha prime x24. And you see, U13 is literally Z2 in this gauge fixing. U24 is literally 1 minus Z2. They add up to 1. That's the first thing. And I can even use Y to express it. U13 is Y over 1 plus Y, and U24 is 1 over 1 plus Y, where I'll choose this base triangulation. That's my Y sitting here, okay? So like 1, 2, 3, 4. The rule I'm going to teach you in general will give you this formula. So it expresses the 2U in terms of this positive thing. You see, it's very nice that when Y goes from 0 to infinity, both U's are between 0 and 1. So that's also a general property of these U equations that I forgot to say. So all the U variables, so the U are manifestly positive rational functions of positive parameter Y. So all the U variables are positive. Okay? And they satisfy U equation, which means they are between 0 and 1. Okay? So the U equation tells you they are between 0 and 1. And what do I mean by binary geometries is that really when you take any U to 0, okay? So the boundary of this space is really parameterized by every U goes to 0. That's the boundary of my of this space. When you take any U to 0, all the U C prime where the intersection number is bigger than 0 will goes to 1. So all the crossing guys will go to 1. And why is U go to 1 important? Because when U goes to 1, it decouples from this U equation. So this is what I mean by binary geometry, and the surfaces will start to factorize, you can see, right? Because so when you go to any curve, say any curve when the U goes to 0, all the crossing guys, every crossing guys goes to 1. So they completely decouple from the system. So you can imagine that the surface become product of two things, where you have the U's on this side and U's on that side. I mean, this is not just true for the disk, for the tree level case, but also true for any surfaces because of that U equation. So that's why I said the U equation is really crucial. From this string integral that I introduced here, I can also explain what is the isosceles now. So the string integral is really, this disk string integral is really giving you a stringy version of the polytope isosceles. So yeah, I haven't explained what is the isosceles. So isosceles is really a combinatorial way of encoding all the trace phi cube diagrams, the trace phi cube amplitudes actually at tree level in a polytope. Okay? So for example, for 4-point, the isosceles is just a line interval. I mean, combinatorially, the isosceles is line interval where this endpoint represents x13 equals 0, this endpoint represents x24 equals 0. And at the 5-point, it's a pentagon where every vertices is a triangulation of a pentagon, and every edge or every codimension 1 boundary is something goes to 0, right? x13 to 0, x14 to 0, x24 to 0, x25, and x35. Okay? And 6-point will be a 3-dimensional polytope that I won't draw here. But every facet of this polytope, codimension 1 boundary of a polytope corresponding to a chord sent to 0, and then every codimension 2 corresponding to 2 non-intersecting chords going to 0 at the same time until you reach the vertices, the 0-dimensional boundaries. Those vertices corresponding to n-3 chords goes to 0 at the same time. So that's a triangulation. Okay, so the isosceles is really a polytope that has n times n-3 over 2 facets. So those are the xij's, and all the way down to Catalan number of vertices. So for 5-point, there are 5 vertices. For 6-point, there are 14 vertices associated with the 14 triangulation I drew before here. So it's a really fun game to play with the combinatorics of this isosceles. But I want to say that this integral actually represents a stringy isosceles. It's not totally obvious here, but if you look at this equation, so when I send xij to 0, what happens? When I send xij to 0, the dominating thing so why the amplitude develop a pole when xij goes to 0? So this is, by the way, this is totally not obvious from the original Koba-Nielsen formula. If I'm asking you, I give you this formula, what are the possible singularities of the resulting meromorphic function? I mean, even just field theory limit, even just take alpha prime to 0, what are the singularities? It's very hard to compute, right? I mean, the thing is Zij raised to Sij, and the singularity happens when either 2 or 3 or more Zij collide, when they degenerate. So you need to blow up really this space. But if you translate to this form, everything is very clear, because all the possible singularities are given by a particular xij goes to 0. When that xij goes to 0, the forces, the dominating part of the integral is given by the corresponding uij goes to 0. And what's the behavior there? When uij goes to 0, as I just said, all the crossing ukl goes to 1. So the disk immediately factorized. So this uij really give you a blow up of this disk, right? It's manifesting all the boundaries, all the singularities of this. So what is this singularity structure of this modular space of this disk with n mark points? It's the Surfaceology, right? So you can have one xij equals to 0, which are the facets, codimension 1 boundary. You can have 2 non-intersecting ones to go to 0, then you go to the boundary of a boundary, and so on, until you have all n minus 3 of them go to 0. The whole integral localizes, becomes a 0-dimensional integral, right? So this formula is not only telling you that at field theory limit alpha prime to 0, you obtain the ABHY Surfaceology here. Yeah, I haven't explained this, but also tells you that at finite alpha prime, the string integral factorizes exactly as the Surfaceology does, right? So how does Surfaceology factorize? If I give you an n-gon, you go to the ij, you go to the xij to 0 pole, the Surfaceology factorizes into the product of 2 lower dimensional Surfaceology associated with this subpolygon and this subpolygon, right? So for 5 point is trivial. When you send one xij to 0, so like if you draw the original pentagon, 1, 2, 3, 4, 5. When you send this guy to 0, it factorizes into a triangle times a quadrilateral, right? 3-point amplitude times 4-point. Where 3-point amplitude is trivial, it's 1. 4-point amplitude is a line interval. So you see, the boundary of 5-point amplitude are 5 line intervals. For 6 particle, you can play yourself. That's another exercise if you want. There are 2 kinds of chords, inequivalent chords. One is like this, right? 1, 3. If you go to 1, 3 to 0, it factorizes into 3-point times 5-point. What does it mean? It means that facet is a pentagon, because a 5-point amplitude is a pentagon. The Surfaceology, 2-dimensional Surfaceology for the 5-point one is a pentagon. But you can also go to this boundary, this long diagonal. It divides the hexagon into 4-point times 4-point. What is a 4-point Surfaceology? It's a line interval, right? So that means that those boundaries associated with longer diagonals are quadrilaterals. They are line interval times line interval, right? So I didn't draw it, but if you is something you can draw on a piece of paper, that the 3-dimensional Surfaceology is a polytope with 9 facets, where 6 of them look like pentagon, 3 of them look like quadrilateral. So try to draw that thing, and the three quadrilateral correspond to long diagonals, and the 5 pentagon corresponding. Sorry, six pentagons corresponding to the shorter diagonals. And all I'm saying here is that the uij variables make this property even manifest for the whole string integral, because whenever xij goes to 0, the whole string integral, without taking alpha prime to 0, the whole string integral just factorizes into 2 lower point string integral, associated with the subpolygons.
By the way, can you spell the what if? Can you spell the Surfaceology? For I can take a note.
Sorry, can I?
Can you also spell it for us?
Oh, sorry. Okay. So sure. I mean, originally it was a combinatoric structure with how you pair the brackets, right? So that's why it's called a Surfaceology. And combinatorially, we know it has to do with this trace phi cube tree amplitude, because the combinatorial structure is associated with trivalent graphs, planar trivalent graphs. But it's really what I'm trying to explain here is that not only the field theory limit, alpha prime to 0 limit, is given by a ABHY isotropy, but also the string amplitude can be viewed as a finite alpha prime version of the isotropy. Okay, I think I'll probably stop here and take 4 more questions. Thank you. What is gauge invariant? I didn't get the first. Yes, the gauge invariant, I mean SL2 invariant here. So the Z variable, you have n punctures. It's very Z variables are very nice because they are each puncture associated with a Z, right? But there are 3 of them you can fix because there's a redundancy, this SL2 redundancy. But in terms of Y, the U in terms of Y becomes completely gauge invariant. There's no, so that's also a very important point about surfaceology. Instead of focusing on all these external particles, we're focusing on the curves. So the curves are the basic thing. So we're really taking all the curves, and for every curve I have something. So that's for the disk, that's a fundamental thing saying that I have only every curve, every chord ij, I have a uij, and the uij depend on n-3 independent variables because of these u equations. I solve u equation. One way to solve them is to express them in terms of n-3 y's. So that trivialize this gauge redundancy. Because I've stopped focusing on all the z on the boundary, there's no SL2 for me. So everything, because you can also see that u is cross ratio. So there's nothing dependent on the SL2 fixing and so on. So that's an important point. Yeah. Thank you.
While determining the number of independent extended variables, we also take into account the Amplitude conditions depending.
No. Sorry. So I should say from the very beginning that this when I consider trace phi cube amplitude, I'm really imagining myself living in infinite number of dimensions, or the space-time dimension is larger than the number of particles, so that all my xij are independent. There's no gram determinant or anything. Yeah. Yes.
Is there a way to draw the string via associated?
No. Yeah. Very good question. Strictly speaking, I haven't really explained what's the relation of this with association. In the next lecture, I will do that. It cannot be drawn. It's really the boundary structures look like the association where every uij, but the uij's are nonlinear variables. They are not like a flat polytope associated with it. So you can really, the simplest way to see this is really you look at for 5 particles, you look at the original z variable, it looks like a triangle. But when you use the 5 u variables, it blow up that triangle into a curvy pentagon. So it's a very it depends on how you parameterize it. But the combinatorics looks like a tetrahedron, but it's really curvy. Yeah.
Now let me speak again.